All right. So we got 11.6 to talk about. So there are 3 videos for 11.6 that I've broken down, so it's not like you have to watch a giant long video of me yapping at you. So the first video is going to be about the complement of an event. The complement means that the event does not occur. Okay? The event does not occur. And we show the complement by either saying like not E, so you'll see me write a lot of not E. Or if you want to relate it back to when we did Venn diagrams, it'd be E with the apostrophe. So there are 2 quick formulas that we can talk about when we talk about the complement of an event. We can talk about the probability of not E, or again, relate it back to your Venn diagrams. Well, if you want the probability of not E, all you got to do is take 1 minus the probability of the event actually happening. Okay? Or you can kind of reverse that. If you want the probability of an event actually happening, you can take 1 minus the event not happening, the probability of it, of course. Okay? Again, these are just formulas. They are suggestions. You can always figure out the probability of an event not happening, the complement, in other words, the regular way by thinking about how many ways can this happen and then over the total. You can always go back to basic probability with this. And speaking of basic probability, everything in 11.6 is all basic probability. You shouldn't have to use any fundamental counting principle. You shouldn't have to use any permutations or combinations. So this is all going to be basic probability of what we want out of the total. So let's do some examples. Okay? So I have an example here that says you are dealt 1 card from a 52 card deck. I probably should have the word A in there, but it's been a long day, so my bad. So you are dealt 1 card from a 52 card deck. Find the probability that you are not dealt a 3. So we want the probability of not 3. Well, if I want to talk about those formulas, it's a little bit easier to think about it as 1 minus the probability of a 3 actually happening. Okay? So, let's talk about this. 1 minus, well, what is the probability of a 3 actually happening? Well, how many 3s are in a deck? There are 4. The 3 of diamonds, 3 of hearts, 3 of clubs, 3 of spades. Out of how many cards are there? 52. So you go into your fancy dancy calculator and you let the big dog eat. You let the 1 minus the 4 over 52 happen. Okay, and your calculator will kick out the reduced answer. But I want to talk real quick about what is this actual number. Here's an easy way to figure out what this guy actually ends up being. Of course, it will be over 52 when you actually do the 1 minus the 4 over 52. If you want to figure out this top number here, and this top number actually ends up being the not 3. So if you want to figure out how many ways we can not get a 3, take the 52 minus the 4. Because that will tell you how many cards are not 3. Because there's only 4 cards that are 3. So if I take 52 minus 4, you get 48. And that reduces down to, when you actually go to the calculator, of 12 out of 13. That's the real answer I'll be looking for. And again, they want fractions throughout this thing. They want fractions. So, here's another one. So this time, they're actually giving you a table of values. So in this one, our table is about the age distribution of U.S. moviegoer audiences. Okay? And we have 12 to 24s. There were 900 of them. 25 to 44, there were 1,080 of them. 45 to 64, there were 840, and 65 to 74, there were 180. So before you can even approach this problem, if you have a table, just like before when we had tables, get the total. If you add all 4 of these numbers up, you end up with 3,000. So that is our denominator when we're dealing with probability in this. So here, it's asking if one moviegoer is randomly selected from this population, find the probability that the moviegoer is not in the 25 to 44 age range. So, things are jumping around. Love it. let's start finding this probability. So we want the probability of not 25 to 44. Well, why don't we just look at 1 minus the probability of 25 to 44? Although it's not hard to figure out this probability without doing this part right here. Again, it's just a suggestion to use this. If you like going the other way and getting all the information without having to go through this, it all works the same way. So, what is the probability of being 25 to 44? Well, how many were there? There were 1,080. Out of how many were there total? 3,000. So again, you can go to your fancy dancy calculator, let the big dog eat, jump straight to the answer. But again, if you actually wanted to figure out what this probability was, take 3,000 minus 1,080. And if you subtract those two, you end up finding out that there are actually 1,920 people that were not 25 to 44 out of 3,000. But again, you went to your calculator, woo, stuff is flying around. If you went to your calculator and you figured out this information, that was 16 out of 25. Okay? So, I have 3 problems now that I want you to try on your own. Okay? Because it is your turn. So, I got 3 problems. Like I said, we're going to go 1 problem at a time. So I'll show you the problem, read it real quick, then you'll pause the video, give it a shot, and then watch the video to see how it worked for you. And then I'll show you the next problem, you'll pause it, give it a shot, watch the video, then I'll show you the final problem, pause it, give it a shot, watch the video. And then you can move on to the second one after that. So it says you are dealt 1 card from 52 card deck from a 52 card deck. Find the probability that you are not dealt a heart. Go! Alright, so we want the probability of not a heart. So, that's the same as looking at 1 minus the probability of a heart. Well, what is the probability of a heart? Well, how many cards are a heart? There are 13. Remember, you have the ace, 2, 3, 4, 5, 6, 7, 8, 9, 10. Jack, queen, king. That's 13 cards. Out of how many? 52. So again, you go to your calculator, you let the big dog eat. If you actually figured out what the probability of not a heart was, you'd have 39 over 52. But that just reduces down to 3/4, which is what I'm looking for. Okay, here is the next problem. Try it. Oh, you are dealt 1 card from a 52 card deck. Find the probability that you are not dealt a red picture card. Now try it. Okay. So what is the probability that it is not a red picture card? So that's what RP, red picture card. Because I'm lazy and I want to abbreviate. 1 minus, well, what's the probability of actually getting a red picture card? So, 1 minus, how many red picture cards are there? And there are a total of 6 out of 52. There are 6 because you have the Queen of Hearts, the Queen of Diamonds. You have the King of Hearts, the King of Diamonds, and the Jack of Hearts and the Jack of Diamonds. So you go to your calculator, you let it do its job, and you figured out that your answer, or if you actually found the not RP, would have been 46 out of 52. Which reduces to 23 out of 26. And there you go. So 1 more problem, and we're going right back to that chart that I gave you from the beginning. So this is the same chart. Give you a moment to look at it. And then the probability that we're after, this is what we want to know. If one moviegoer is randomly selected from this population, find the probability that the moviegoer is less than 65. Try it. Okay. So, if you are less than 65, that means we want the probability of not being 65 or older. That's what it really means. When you're saying less than 65, you are not 65 or older. So let's take a look at 1 minus the probability of being 65 and older. Again, remember on this, the total was out of 3,000. So how many people were 65 and above? If you go back up to the top and look, you should have found out that it was 180. And if you actually reduce this down, here is the real probability of not being, sorry about put a 9 there, should be 2,820. That's how many that are not 65 and above out of 3,000. But of course that reduces down to, and if you let your calculator do the work a moment ago with the 1 minus the 180 over 3,000, you get 47 over 50. Okay, so move on to the next video. Welcome back for round 2. So this time we're going to dive deeper into probability. Again, we're still working with basic probabilities here, so no permutations, no combinations, no fundamental counting principle. But we're going to talk about OR probabilities. Now, in order to talk about OR probabilities, we need to get a definition under our belt, which is what we call mutually exclusive. What mutually exclusive means is that two events cannot happen at the same time. Those events would be mutually exclusive if they cannot happen at the same time. For instance, like flipping a coin. If you flip a coin, you can either get heads or you can get tails. You cannot get heads and tails at the same time. So flipping a coin is what we would call a mutually exclusive event because they cannot happen at the same time. Same thing with like running a race. When you run a race, you cannot get first place and second place at the same time. It's impossible. You either come in first or you come in second. So running a race and your place that you finish in a race, that is mutually exclusive because you are one and only one place in a race when you finish it. Okay, your first, your second, your third, your fourth, your fifth, whatever, so on and so forth. You can't occupy more than one piece. Same thing with rolling a die. If you roll a die, your answers are only 1, 2, 3, 4, 5, 6. So it's not like I can roll a die and I can end up with a 1 and a 2 at the same time. I either roll the 1 or I roll the 2. So that's what we mean by mutually exclusive events. They cannot happen at the same time. Let me give you an example of not mutually exclusive, kind of set the idea for this. Cards. Cards can generate not mutually exclusive events. For instance, like say I had a deck of cards and I wanted to pull out a 7 or a red card. Now that is not a mutually exclusive event because there are cards that are both 7 and red. So that breaks the idea of mutually exclusive because I can have a 7 and a red card at the same time. You got the 7 of hearts, the 7 of diamonds. So that's what it means to be mutually exclusive. They cannot happen at the same time. If the events can happen at the same time, then that means they are not mutually exclusive. So with that information, then we can talk about OR probabilities because OR probabilities are split up into two different ideas. There's the probability if they are mutually exclusive. So you've got the probability of A or the probability of A or B. And again, we can relate it back to Venn diagrams that we talked about. ORs and Venn diagrams were the union. So if I want the probability of the union of two sets, then I'm just looking at, and if they're mutually exclusive, I'm just looking at the probability of the first set plus the probability of the second set. Okay? but if the events are not mutually exclusive, okay? So the events can happen at the same time. What you see here is we get an added piece where we have to subtract off those that are in common. So that's the probability of A and B. And then you can see the intersection sign right down here of A intersect B. And again, the reason why we have to subtract that out is because when you figure out the probability of A and you figure out the probability of B, you are basically adding the same idea twice. So kind of going back to that idea of 7 and a red card. When I look at the probability of A, then I already have the 2 red 7s figured into that. When I look at the probability of B, which would be the red cards, I would have both of those 7s figured into it that are also red, which is why we have to subtract out the doubles. Okay? And that will bring you back down to the basic probability. So that's the one thing you have to worry about with OR probabilities, is you have to make sure before you do anything, before you attack this problem, you have to know what kind of problem you're dealing with. Is it mutually exclusive or is it not mutually exclusive? Because there's 2 different formulas that you have to run. Okay? So let's go and do some problems. So it says you randomly select one card from a 52 card deck. Find the probability of selecting a 2 or a 3. So we want the probability of a 2 or 3. So you have to ask yourself this question. Is it possible to draw a card and you end up with a 2 or a 3 at the same time? Can 2 and 3 happen at the same time? And no, that's impossible. When you draw a card, you either draw a 2 or you draw a 3. You can't be both. So this is an example of mutually exclusive. So all we need is the probability of 2 plus the probability of 3. Well, what is the probability of 2? Well, there are 4 2 cards out of 52. What's the probability of 3? There are 4 3 cards out of 52. And then again, you can just go to your calculator, let it do the work, or you can do some quick adding and subtracting here. Here's what's cool about the mutually exclusive, not mutually exclusive, or probabilities. Your denominators are all going to have the same, they're all going to be common already. So you can easily just add these 2 fractions together. 4 plus 4 is 52. And thus, you have everything that you need right there. All you got to do is reduce it. And 8 out of 52 reduces down to 2/3. Or, sorry, not 2/3, 2/13. So, moving on to the next guy. Here it says the mathematics faculty at a college consists of 8 professors, 12 associate professors, 14 assistant professors, 10 instructors. If one faculty member is randomly selected from the find the probability of choosing a professor or an instructor. All right, so we're looking at the probability of getting a professor or an instructor. So the question I ask you is, can you be both a professor and an instructor at the same time here at this place? And the answer to that is no. You are either a professor or you're an instructor. It's 2 classifications at this college, and you have to be one or the other. You're not both. So this is a case of mutually exclusive. So all we need to do is figure out what the probability of a professor is plus the probability of an instructor. So again, before you can do anything though, you need to figure out the total. Easy way to get the total? Add up all your numbers, because this is how many people we're dealing with in this department. Okay? So if I take 8 plus 12 plus 10 plus 14, you end up finding out that there are 44 faculty members in the mathematics. So you already know that both of these guys have to be 44. So all we got to do is figure out their probabilities. Well, how many professors are there? There are 8. How many instructors are there? there are 10. So you can do some quick math because it's already common denominators. So there's your probability, but of course you always reduce. So 9 out of 44 gives us, 18 out of 44 gives us 9 out of 22. All right, next problem. So here, kind of going back to the cards again, it says you are dealt one card from a 52 card deck. Find the probability that you are dealt a 7 or a red card. Hey, does this sound familiar? Yes. So we want the probability of a 7 or a red card. We talked about this a moment ago. Is it possible to pull a card out and be both 7 and red? And the answer is absolutely, because there is a 7 of hearts, which is red, and a 7 of diamonds, which is red. So this is a not mutually exclusive event. So what we have to look at is the probability of a 7 plus the probability of a red, and we're going to subtract out the probability of all those red 7s. Okay? So we already know all the denominators for this. It's all out of 52 if you haven't figured that out yet. So let's just get the probabilities. So what's the probability of pulling a 7? Well, how many 7s are there? There are 4. 7 of hearts, 7 of diamonds, 7 of spades, 7 of clubs. How many reds are there? Well, there are 2 suits that are red. There are hearts and there are diamonds. And there are 13 cards in each, so that makes 26 red cards. Now, what's the probability for a 7 red? Well, there are only 2 red cards that are 7s. And I talked about those earlier, which are the 7 of hearts and the 7 of diamonds. So all you have to do is just go through, do some fancy adding and subtracting. And when you take 4 plus 26 minus 2, you end up with 28 out of 52. But of course, this reduces down to 7 out of 13. And there's your probability. So I got one more that I'm going to walk through with you. Then I've got 4 other problems I want you to try on your own. Okay? So again, this looks a lot like what we just talked about a moment ago. It says the mathematics department of a college has 8 male professors, 11 female professors, 14 male teaching assistants, and 7 female teaching assistants. If a person is selected at random from the group, find the probability that the selected person is a professor or a male. So on this one, we want a professor or male. So if I think about this situation, is it possible to be both a male and a professor at the same time? Well, I would hope your answer would be yes. So this, again, is a not mutually exclusive event because you can be a professor and a male at the same time. It tells you right up there how many there are. So what we need to do then, since this is not mutually exclusive, we're going to find the probability of being a professor. We're going to add that with the probability of being male. And then we need to subtract out all the probabilities of being a professor that is male. Okay? So, first things first, just like what we had to do a moment ago, we need to add all of our numbers up. So 8 plus 11 plus 14 plus 7. That ends up being a total of 40. So all of our denominators are 40. So now all we got to do is just get the top piece. So how many professors are there? Well, this one, got to be careful because now you got to take 8 and 11 and put those together because there are male professors and female professors. And if you take 8 and 11 and put that together, you get 19. And then from there, we got to talk about, well, how many males are there? Well, we've got 8 males and 14 males. So 8 male professors and 14 male teaching assistants. So again, if you add those two together, you end up with 22. And then the last part, how many professors are both male and professors? So there are a total of 8 of those. You actually didn't have to work very hard for that number because it was given to you. So here's what we got. There's all of our probabilities. All we have to do is add 19 and 22, subtract 8, and you end up with 33 out of 40. And that is the answer because that cannot reduce. Okay, so like I said, I have some problems for you. It's your turn. Okay, I got 4 problems, a lot like what we just dealt with. 2 of them will be mutually exclusive, 2 of them will not. So be careful when you're going through these and think about what you're dealing with. Here we go. Here is problem number 1. You randomly select 1 card from a 52 card deck. Find the probability of selecting a red 7 or a black 8. Try it. Okay, so what you should have found out is that this is a mutually exclusive event because you cannot be a red 7 or a black 8 at the same time. So all we need is the probability of a red 7 plus the probability of a black 8. So all these are out of 52 because there are 52 cards. There are 2 red 7s and 2 black 8s, which give us 4 out of 52. And that will reduce down to 1 out of 13 as the probability of drawing a red 7 or a black 8. Next problem, here you go. So a political discussion group consists of 30 Republicans, 25 Democrats, 8 Independents, and 4 members of the Green Party. Excuse me. If one person is randomly selected from the group, find the probability of choosing an independent or a green. Try it. Okay. So, hopefully if you're thinking about this, can you be independent and green at the same time? And the answer is no. So this is a mutually exclusive event. So all we have to do is figure out the probability of being independent and add that with the probability of being green. Okay? So, just like before, you got to figure out how many people you have. So you're going to take your numbers of 30, 8, 25, and 4, add it all up, and see what you get. And when you do add those up, you end up with a denominator this time of 67. Okay, so what is the probability of being an independent? Well, how many independents were there? There were 8. What is the probability of being green? How many greens were there? There were 4. So all we have to do now, add our 2 fractions up. 8 plus 4 gives us 12 out of 67, and that does not reduce. Okay. 2 more problems. You are dealt 1 card from a 52 card deck. Find the probability that you are dealt a heart or a picture card. Give it a whirl. Okay, so we need the probability of being a heart or a picture card. If you thought about this, is it possible to be a heart and a picture card at the same time? And the answer is yes. You have the King of Hearts, you have the Queen of Hearts, you have the Jack of Hearts. So this is a not mutually exclusive event. So what we're looking at is the probability of being a heart plus the probability of being a picture card, but we have to subtract off the probability of being those heart picture cards that we just talked about. So again, denominator is all 52 because we're dealing with 52 cards. So now let's talk about their top numbers. How many cards are hearts? Well, there are 13. And again, I mentioned all those earlier. Ace, 2, 3, 4, 5, 6, 7, 8, 9, 10. Jack, Queen, King. So there are 13 of those cards. How many picture cards are there? Now remember, our picture cards are Jack, Queen, and King. And every suit has those picture cards. So there are 12 picture cards total. Now, how many picture cards are hearts? There are 3. Jack of hearts, Queen of hearts, King of hearts. Okay? So, there's all of our probabilities. All we have to do now is do the adding across the top and the subtracting, of course. And if you add all those together, you get 22 out of 52, which reduces down to 11 out of 26 for our probability. Okay? One more problem. So the mathematics department of a college has 8 male professors, 11 female professors, 14 teaching assistants, and 7 female teaching assistants. If a person is selected at random from the group, find the probability that the selected person is a teaching assistant or a male. You're up. Okay, so if you thought about this, this is a not mutually exclusive event because you can be both male and a teaching assistant. So we need the probability of a teaching assistant or the probability of a male. So again, this is not mutually exclusive. So we get that probability of the teaching assistant, add that with the probability of a male, but we need to subtract off the probability of a teaching assistant that is male. Okay? So you already know the denominator for all these. We did this problem together a couple minutes ago. So the denominator for all this was 40 when we added all those numbers up above. Okay, so now all we got to do is just figure out how many teaching assistants there were. So there were 14 male teaching assistants, 7 female teaching assistants. If you add those two up, you end up with 21 teaching assistants. Then you got to figure out how many males are there. Well, we have 8 males and 14 males there. So that adds up to a total of 22. And then give me the probability for the teaching assistant and male. How many were there? Woo! Again, everything's moving around on me. And that's this guy that's right here. There were 14 males that are teaching assistants. So we slap the 14 right there. And we go and do our adding and subtracting across. And your top number ends up being 29. And again, that will not reduce. And there you go. Go ahead and get ready for the last video of 11.6. Okay, this is it. This is it. The last video. Then you are completely responsible for the homework for 11.6 and the quiz, because this will wrap up that trio of sections there so you can get this done. So all we have to do is talk about odds. Odds, now this is what Vegas is famous for. So if you go to Vegas and things like that, and you talk to casinos, actually just casinos in general, I should say. Casinos in general are famous about their odds. They will tell you the odds in favor of you winning certain games. Okay? So now we're going to explore, what do odds really mean? So Odds up here, there are two ways to figure odds. You can talk about odds in favor, which is what usually people deal with and what you mostly see, or we can talk about odds against. So up here, you see the basic formula for odds. The odds in favor is the probability of the event happening over, wow, I'm controlling it all on its own. The probability of the event happening over the probability of the event not happening. And then the odds against just flips it. So if you know the odds in favor, you actually know the odds against, because all you got to do is take the reciprocal, which means flip the fraction. Okay, odds, just like other probabilities, are reduced fractions. There are lots of ways to write odds. So you can write them as fractions. Sometimes you'll see them written as a number colon a number. Sometimes you'll see them written as a number to a number, like 1 colon 2, or your odds are 1 to 2. Okay, so you hear a lot of people, usually in casinos, you'll hear this. For our homework, we're going to stick to the fraction, and again, we always reduce it. Now, let me basically kind of break down odds. Now, they talk about probabilities over here, and I'll show you the probability piece, but I think it's a little nonsense to talk about the probability piece. Okay? So here's how I really think about odds. When we're talking in favor, and I generally talk about the in favor, because if I want the ones against, I just flip the one that's in favor. When we talk about the ones in favor, what goes on top are all the outcomes you want. Think about it as all the outcomes you want. The number of ways you can win. Okay? On the bottom goes all the outcomes you don't want. Okay? That's really what odds are about. On top are all the outcomes you want. So like say we're rolling a die, and the only way I win is by rolling a 2. Okay, so I'm rolling a die. The only way I win is by rolling a 2. Well, how many outcomes do I want? There's only one. It's 2. So on top is the number 1. How many outcomes do I not want? Well, I want to make sure that none of the other numbers pop up. So I lose if a 1 pops up. I lose if the 3 pops up. The 4, the 5, the 6, all of those are losers. Okay? So how many outcomes are there that I don't want? There are 5 of them. Because if the 1, the 3, the 4, the 5, and the 6 pop up, I've lost. The only way I win is if the 2 pops up. So the odds in that situation would be 1 to 5, or 1 over 5. Because there's only one outcome where I win, but 5 where I lose. So keep that in mind. That makes odds a little bit easier than working with the probability. And again, I'll show you the probability and what it looks like, where if you just think about it like what I told you over here, all the outcomes you want over all the outcomes you don't want, makes things a whole lot easier. So I've got 4 problems. 2 I will work together with you, and then 2 you will try on your own. So here it says 1 card is randomly selected from a deck of cards. Find the odds in favor of drawing a heart. So we are in favor of a heart. So let's talk about those odds. So again, talking about it my way. So on top, how many hearts are there? That's how we can win. So how many hearts are there? And we talked about this on the last video. There are 13. There's the ace of hearts, the 2 of hearts, the 3 of hearts, the 4 of hearts, 5 of hearts, 6, 7, 8, 9, 10 of hearts, jack, queen, king of hearts. So there are 13 cards where I can win. How many cards are there where I can lose? Well, if you want to think about this bottom guy, all you got to do is take the total number of cards minus what you wanted to win from above, and that will tell you this bottom guy. So there are 52 cards. 13 cards allow me to win. So if I subtract those 2, that means that there are 39 cards where I will lose. Okay? So again, 13 ways to win and 39 ways that I can lose. And of course, we always reduce this. So if I reduce this down, my odds really are 1 to 3. My odds are 1 to 3. Now, let me show you the probability way, which again, it's just silly if you just think about what we're doing. Okay? So they want the probability of a heart over the probability of not a heart. Okay, so what is the probability of a heart? Let me scroll up a little bit. Sorry, I'm grabbing the wrong thing. Let me scroll up a little bit. So, what's the probability of a heart? Well, that's 13 out of 52. What's the probability of not a heart? Well, there are 39 cards that are not a heart. Okay? So this is what it looks like going through their formula. But remember, we don't really divide by fractions. Remember, we've got that KCF. Keep, change, flip. So we're going to keep the top guy. We're going to change from the division to multiplication. And we're going to flip the bottom guy. And if you remember anything about multiplying, if you have a number on top and a number on bottom that are the same, they just cancel each other out. So what does that leave you with? 13 over 39, which is what we just talked about. So that's why I say go with what I'm talking about. Think about all the ways you can win over all the ways you can't. And if you want to do the against, all you do is just flip that. All the ways you can't win over all the ways you can. So let's take a look at an against problem. So one card is randomly selected from a deck of cards. Find the odds against a 9. Against 9. So I always start with the ways that I can win. And this time, because we're going against, that means the ways that I can win, they need to go in the denominator. Okay? So how can I win? Well, how many cards are there that are 9s? There are 4. How many cards are there that are not 9? So remember that trick I just taught you. Take the total minus the what you want, or the ways to win. So that's 52 minus 4. So that gives you 48 over 4. But again, we got to reduce our odds. So if we go to our calculator and reduce that down, you end up finding that your odds are 12 to 1. 12 to 1. Okay. So, your turn. I've got 2 problems left. One that talks about in favor of, and one that talks about against. Let's do this. Let's finish this up. So, one card is randomly selected from a deck of cards. Find the odds in favor of drawing a red card. Do it. So, the odds in favor of a red. So, on top goes the ways that we can win. How many red cards are there? There are 26, because you have 13 hearts and 13 diamonds. How many ways can we lose? Well, if I take 52 minus 26, we get 26 again. And that makes sense, because there are 2 sets of black cards with each 13 in them. So if I reduce my odds, what are the odds in favor of drawing a red? It is 1 to 1. And I didn't mention this on the previous problem, that was 12 to 1. You do need the denominator of 1 in there. And in this one, you need to write it as 1 over 1. That is super important. These are odds. Odds are made up of 2 numbers. Kind of like when you were dealing with slope. Slope had to be 2 numbers. So one more problem, and then we are all done with 11.6. So one card is randomly selected from a deck of cards. Find the odds against drawing a black king. Okay, here we go. Last problem. So we are against the Black King. So, on top are all the ways that we're not going to win. On bottom are all the ways that we can win. So how many ways can we win by drawing a Black King? Well, how many Black Kings are there? There are 2. The King of Clubs and the King of Spades. How many ways can we lose? There are 50. Because 52 minus 2 is 50. And if we reduce this down, the odds against drawing a Black King are 25 to 1. So that is it. It is all up to you now to complete the assignment and complete the quiz. Thanks.